Good day, we are Group Priori, and today we'll be showing you how we predicted song virality using machine learning. So, first we will go through the 4 steps of the project, from problem formulation and data collection to data pre-processing and visualization, model training and evaluation. Then we'll finally deploy the machine learning endpoint and demonstrate an API call. For our project, we decided to use the Spotify most streamed songs dataset to gather insights regarding the musical attributes and track information of various songs, such as track name, album name, artist name, danceability, energy, and tempo. With this dataset, the group aimed to identify factors that contribute to a song's virality, allowing record labels and streaming platforms to fine tune their marketing strategies, leading to data driven solutions. So, why use machine learning? We decided to analyze the dataset using machine learning due to the multifactorial influences as a song's popularity is dependent on various measurable features. The value of machine learning as it learns the patterns from historical data to predict future success, the approach of using supervised learning through regression analysis, and the target output. So, to further align the business problem and the use of machine learning, we wanted to solve the business need by forecasting song virality for strategic promotion while using historical song data to predict future stream count or for identifying potential viral hits.
Before the model was trained and evaluated, the group applied data pre-processing steps such as handling missing values, removing unnecessary columns, converting of data types, and removing of outliers. To address the missing values, the function isNull was used to identify them. After identification, the function dropNA was used to finally remove the missing values, and then afterwards, we removed the cover URL column because the group identified that this feature was not necessary for the training of the model, as it was simply a link to an image. After this, we then checked the data types of each columns and found out that some columns had incorrect data types. We then converted these columns to the proper corresponding data types, and then after we removed the rows that resulted in null values after conversion. Lastly, we removed some outlier songs from the dataset that had streams less than 1 million. After cleaning our dataset, we applied exploratory data analysis. Using a heat map, we were able to explore the correlation between the different features. We observed that out of all the musical characteristics, valence had the highest correlations to the number of streams. However, it is to be noted that this still had a low positive correlation. Out of all the correlations, energy and acousticness had the lowest correlation, with a strong negative correlation of negative zero point 0.8. One discovery we also noticed was that songs released in the past 10 years have more streams than those from the other years. Also, the month of May was a popular month for song releases. On the other hand, the month of August saw the fewest number of releases.
Next is we split our dataset into 70% training, 15% validation, and 15% testing. This split was randomized once to avoid bias and ensure generalizability. So randomization helped avoid any patterns in the data order that could skew the results. So next, we use 3 models. The first one is the linear regression. This model is great for interpreting how individual features like beats per minute, danceability, or energy influence stream counts. So it gives us coefficients that are easy to interpret. Next is decision tree regressor. This model lets us follow a logic tree from root to leaf to see how combinations of features might predict popularity. Lastly is the random forest regressor. By combining multiple decision trees, we hope to improve accuracy and better identify which features are constantly important. So to evaluate performance, we use 3 key metrics. First is the mean squared error or MSE, which penalizes large errors more, helping us see how far off we were. especially on very popular songs. Next is the mean absolute error or MAE, which gives us an average of how many streams we missed by making it more intuitive. Lastly is R squared. It tells us how much variance in stream counts is explained by our model. Now, the results. For our linear regression had nearly perfect R squared and almost zero errors in training data, which was suspicious. It turned out the model was overfitting, which is the model is just memorizing instead of learning patterns. Meanwhile, for the decision tree and the random forest, they perform significantly worse, with the MSE in the trillions and MAE in the millions. This meant our predictions were far off, often by millions of streams. So what went wrong? The evaluation showed that common musical features just don't predict streaming success well. Things like energy or tempo, they don't explain popularity. Marketing, artist reputation, and playlist placement are likely more important, but those weren't in our dataset.
So onto the actual model demo. First we saved the linear regression model, which was trained on the first feature set. The first feature set being 10 different features, namely BPM, key, mode, danceability percentage, valence percentage, energy, acousticness percentage, instrumentalness percentage, liveness percentage, and lastly, speechiness percentage. So we added this job lib model to the Google Cloud Storage bucket, and then afterwards we registered it to the Vertex AI Model Registry. Afterwards, we declared the model to be deployed as an endpoint. So this is given by the your model ID variable, which can be found in the Google Cloud dashboard. So onto the actual endpoint creation. This just shows what model we're actually deploying as an endpoint. And then for the sample API call, we use the 10 features as the input. And then this was the response for the Google Vertex API to the call. So based on the 10 input features, we were able to receive a prediction of around 333 million streams. And then this is a sample video. So this is a sample call from the Google Cloud dashboard. So here we were able to see via yung sa prediction, the roughly 333 billion streams. And then this is just the same thing, but we did it via the Google Colab. So yeah, so ideally, the 10 sample features input, those are from a song.
Okay, but here's the most important part. The value didn't end with poor results. Even though our models didn't perform well, the machine learning process still gave us five major benefits. First is it gave us a structured data-driven approach. Rather than guessing, we systematically tested how features relate to outcomes and discovered that most don't. Second is it revealed the limitations of our data. Our poor MSE and MAE scores told us that we're missing important factors, which helps us improve future datasets. Third is we built a reusable pipeline. Every step, from cleaning, modeling, evaluation, can now be reused and adapted for other music datasets or prediction tasks. Fourth is it pushed us to think critically. We learned that measurable traits aren't always influential. Just because we can record danceability doesn't mean it drives streams. Fifth and lastly is it laid a foundation for future improvement. These results aren't a failure, they're a baseline. Now we can iterate, add better features, and refine our predictions. That's all from us. Thank you for listening.